All right, today we're going to do something really cool. Think of it like an engineering project. We're going to build a language model completely from scratch. We'll start with just a pile of raw text and, piece by piece, assemble a real working predictive engine. So let's get our hands dirty and dive right in.
Okay, so every good project needs a blueprint, right? Here's ours. First, we'll lay the foundation. That's our text corpora. Then we'll build the engine itself, the n-gram model. After that, we need a way to measure how well it works, so we'll look at the math and a metric called perplexity. We'll hit a snag, so we'll need a fix. That's smoothing. And finally, we'll step back and look at the whole assembly, from raw text all the way to a prediction machine.
All right, part one, the foundation. You can't build anything without the right raw materials. And for a language model, our raw material, well, it's data. Specifically, a massive collection of text that we call a corpus.
So, what exactly is a text corpus? You might think it's just, a bunch of text scraped from the internet. But it's way more than that. It's a large, structured body of text. Think of it less like a random pile of books and more like a carefully curated library designed for statistical analysis. This is the bedrock, the foundation, where our model is going to learn all the patterns and quirks of human language.
And this is where a huge engineering decision comes in. The corpus you choose literally defines the personality of your model. You train it on something like the Brown corpus, which has a mix of genres, you get a good generalist. But if you train it on the Gutenberg corpus filled with classic literature, your model's going to sound like a 19th century novelist. And if you feed it the web and chat corpus, well, it's going to pick up on all our slang and emojis. The key takeaway here is the fuel you put in totally defines the machine you get out.
Okay, but here's our first real problem. The text we find out in the wild, it's a mess. It's totally unstructured. For a computer, it's kind of like a chunk of unrefined ore. You know there's something valuable in there, but you can't use it as is. It has to be processed first.
And you can see that transformation right here. On the left, you've got that raw, chaotic text, spam messages, normal messages, all jumbled together. But on the right? That's what we want. We've brought order to the chaos by putting it into a structured data frame. It's basically a table. And now, each message isn't just text anymore, it's a neat, analyzable data point. And we do more than just store the text. This is the crucial part. We engineer features from it. Look at those columns we added. Length, haslink, word count. These aren't just random bits of info. They're quantifiable signals that a machine learning model can actually understand. This is literally how we turn language, something fluid and human, into cold, hard math that a computer can work with.
Now, data frames are great, but they're not the only tool in the shed, of course. If your text has a lot of extra info, metadata like authors and dates, something like XML might be a better fit. And if you're dealing with absolutely massive amounts of text that you need to search through, you might turn to a database, either SQL or NoSQL. Like any engineering choice, it's all about trade-offs. You're balancing complexity, flexibility, and the specific needs of your project.
Okay, so let's get you thinking like an engineer. Here's a quick board-style question for you. Imagine you're building a spam classifier specifically for tweets. What kind of features would you engineer? What would you look for? Maybe counting hashtags or mentions? What about checking for those shortened URLs that spammers love to use? Just think about it, because the quality and cleverness of these features you dream up, that's what will make or break your model.
Okay, our foundation is solid. Our raw materials are processed and ready to go. Now it's time for the fun part, building the engine. This is the core of our machine, the part that does the actual work. And the engine we're going to build today is a classic but incredibly powerful one, the n-gram model.
So what is language modeling really? Well, at its absolute core, it's all about prediction. It's about using stats and probability to figure out how likely a sequence of words is. Or, to put it even more simply, if I give you the words, the cat sat on the, what's the most likely word that comes next? Mat? Floor? Chair? It's basically a sophisticated statistical guessing game. And this simple idea, it powers some of the most advanced tech we use every single day.
And believe me, these applications are everywhere. That predictive text on your phone keyboard that finishes your sentences, that's a language model. Google Translate, turning one language into another, yep, language model. When you talk to Siri or Alexa, you got it. And of course, the huge ones like GPT, they're just the biggest, most complex language models we've built so far. This stuff is truly the engine behind modern digital communication.
So how does our n-gram engine actually work? Well, it's built on a really clever and scalable idea. We look at a sequence of n words at a time. The simplest version is a unigram, where n is 1. It's kind of dumb, actually. It just looks at individual words and their probability with zero context. But then we get to a bigram, where n is 2. This is a huge leap. Now we're looking at the probability of a word given the one word that came before it. We have a tiny bit of context. A trigram, as you can probably guess, just widens that window to the 2 previous words. It's a simple hierarchy of increasing our contextual awareness.
Now you might be wondering, why not just look at all the previous words? And the answer is, it's computationally impossible. And that's where this brilliant mathematical shortcut comes in, called the Markov assumption. It's a simple but profound idea. The future behavior only depends on its recent history. It means to predict the next word, we don't need the entire novel that came before it. We just need the last few words. This is a massive engineering trade-off. We're sacrificing perfect long-range memory for a model that's actually fast and practical enough to build.
Okay, we've got the high-level design of our engine. Now it's time to get our hands greasy and look at the math. Let's pop the hood and see exactly what makes this thing run.
So, in a perfect world, if we had infinite computing power, we'd calculate the probability of a sentence using the full chain rule of probability. That means the probability of the first word times the probability of the second word given the first, times the probability of the third word given the first and the second, and so on. It's beautiful, it's perfect, and it is a computational nightmare. The number of possibilities just explodes. It's completely impractical.
And this is where our engineering trade-off, that Markov assumption we just talked about, comes in to save the day. Look at the formula now. We're not using an equal sign, we're using an approximately equal to sign. We approximate. For our bigram model, instead of looking at all the words that came before, we just say, let's just look at the one right before it. It's not perfect, but it makes the problem suddenly manageable.
So how do we actually calculate this probability? Honestly, it's just counting. That's it. The formula looks a little formal, but all it's saying is that the probability of word B coming after word A is just the number of times you've seen A, B together divided by the number of times you've seen A by itself. So for our example, P of MI, we just look at our little corpus. How many times do we see the pair I am? Twice. Okay, and how many times do we see I? Twice. So 2 divided by 2 is 1. Our model is 100% certain that am follows I based on this data.
All right, your turn again. Let's try to calculate the probability of the whole sequence, /s, I am not /s, using our new corpus. You just do what we did before, right? Calculate the probability for each pair, like pi/s, then pi, I, and so on, and then multiply them all together. Seems straightforward, but be careful. This is where we're about to see a huge, critical flaw in our simple design.
And the answer is 0, a big, fat 0. But why? I mean, we saw we saw am not, but look closely. The very last pair we need is not, followed by the end of sentence marker. And that bigram, not slash, well, it never appears in our training data. Its count is 0. And what happens when you're multiplying a chain of numbers and one of them is 0? The whole thing becomes 0. This is what we call zero probability problem. And it's not just a small bug, it's a catastrophic, model-breaking flaw.
Okay, so our engine has a major design flaw. It can just completely seize up. Before we can even think about fixing it, though, we need a way to measure how well or how poorly it's performing. We need a dashboard with some gauges on it. And in the world of language models, our main gauge, our speedometer, if you will, is a metric called perplexity.
So what is perplexity? Think of it as a measure of the model's surprise or confusion. When our model sees a new sentence, how much does that sentence throw it for a loop? If the perplexity is high, it means the model was really surprised. It found the sentence very unpredictable. If the perplexity is low, it means the model was like, yep, saw that coming. It was confident. So the single most important thing to remember is, for perplexity, lower is always better.
Let's see this in action with a success story first. We give our model a test sentence. I am happy. Now, our model looks at its training data and goes, okay, have I seen I at the start of a sentence? Yep. Have I seen am after I? Yep. Happy after am? Yep. It's seen all these pairs before. So for every single bigram in this sentence, it can calculate a real, non-zero probability. And when you take all those probabilities and plug them into the perplexity formula, don't worry about the exact math right now. You get a really low number, 1.316. This is fantastic. This is our dashboard telling us the engine is running smoothly. Our model was not surprised by this sentence at all. It handled it with high confidence. But what happens when we hit a bump in the road? Let's try this test sentence, you am happy. Now it's grammatically weird, but someone might type it. Our model starts off okay. It's probably seen you at the start of a sentence. But then it hits the next pair, you am, and it searches its memory, its entire training corpus, and it finds nothing. It has never seen am follow you. The count for that bigram is 0, and so the probability is 0.
And what do you think happens to our perplexity score when even one of the probabilities in that chain is 0? The whole calculation just breaks. It goes to infinity. Our dashboard needle just slams all the way to the right and shatters the glass. A single unseen word pair makes our metric completely useless. Our model isn't just bad on this sentence, it's infinitely bad. This is a showstopper. We can't ship a product that does this.
Okay, our engine has completely seized up. A single unexpected part, that unseen bigram, caused a total system failure. So it's time to take it back to the workshop for an absolutely essential tune-up. We need to add something that acts like a lubricant for our engine, something that stops these zero probability problems from jamming the gears. And that technique is called smoothing.
So what is smoothing? It's the engineering fix for a problem that is unavoidable with language, data sparsity. What that means is, no matter how much text you have, even if you have the entire internet, you will never see every single possible combination of words. It's just not possible. So smoothing techniques do something really clever. They basically rob from the rich to give to the poor. We take a tiny, tiny fraction of the probability from the word pairs we have seen, and we sprinkle it over all the word pairs we haven't seen. This ensures that nothing, absolutely nothing, ever has a probability of exactly 0. And you can see the fix right here, side by side. On the left, that's our old, brittle formula that breaks so easily. On the right is the simplest, most classic smoothing technique called Laplace smoothing, or sometimes just add 1 smoothing. The logic is dead simple. Look at the numerator. We just add 1 to every single count. So even if the count was 0, it now becomes 1. But you can't just change the top of a fraction. You have to balance it. So in the denominator, we add v, which is the total size of our vocabulary, the number of unique words in our corpus. This simple change guarantees our numerator will never be 0.
Let's apply this to our problem case. Remember that unseen bigram drinks tea? Without smoothing, its count was 0, so its probability was 0. Now, with Laplace smoothing, the numerator is the count 0 plus 1, which is 1. The denominator is the count of the first word, drinks, which was 1, plus our total vocabulary size, which is 8. So 1 plus 8 is 9. Our new probability is 1/9, or about 0.111. Now look at that number. It's small, which makes sense because we've never seen it before. But the most important part? It's not 0. The engine is fixed. It can now handle the unexpected.
All right, let's step back from the workbench for a second and just admire what we've built. We have gone all the way from a messy pile of raw text to a fully assembled, tuned-up predictive engine. Let's do a quick recap of the entire construction process.
First, we sourced our fuel. We got a text corpus, and we structured that raw data so our machine could use it. Step 2, we built the core engine, using n-grams and the clever Markov assumption to make it practical. Step 3, we installed the dashboard, the perplexity metric, to see how well it was running. And that dashboard immediately flashed a big red warning light. So for step 4, we did that crucial tune-up. We applied smoothing to fix the 0 probability problem, making our model robust and ready for the real world.
And that brings us to one final, really important thought. The engine we've built is amazing, but it has a limitation. It's kind of nearsighted. Its window of context is tiny, just 1 or 2 words. It can predict the next word in a phrase, but it has no idea what the theme of an entire paragraph is or the plot of a document. So the real question, the next engineering challenge, is this. How can we build a model that understands the meaning of an entire document? A model that can see the whole forest, not just the next tree. And that very question, well, that's what led to the development of the huge, powerful models like transformers that are changing our world today. But that is a whole other construction project for another time.